Folks, thank you for coming over. We're going to sit down and we're going to have a chat about the world of alkenes. Okay, so I told you to focus on the E, didn't I? E means something different and organic, and what E means is a double bond. Okay, there's the family of compounds that we're going to be talking about in this lecture. It's going to be double bonds. Alkanes with the ANE means single bonds all the way through. All the carbons to carbons were single bonds. Now, please don't get this confused. I did have carbon double bonded to oxygens in the last module. Those were not called alkenes. Those were called something else because it's a different type of functional group. What we are focused on is the carbon to carbon bond. So, alkenes have carbon to carbon double bonds here. Alkanes have single bonds to all of the carbons. So, alkenes, double bonds. We can introduce a formula to you just like we did last time. We rarely use it, but I can at least introduce it to you. CnH2n. Now remember, alkanes were CnH2n plus 2. All right, so that meant if I had 6 carbons, well, 6 times 2 is 12, plus 2 more is 14. So if the structure met this criteria, it was a very, what I would call, good sign. It was not a confirmation. All right, it's a very good sign that it might, there's the key word, might be an alkane. Well, we can do the same thing with alkenes. And there's a double bond that gets formed here, and that double bond represents 2 electrons, doesn't it, right? That extra line is 2 electrons. So what we do is that we take 2n plus 2, and we take 2 away from it, because we are drawing an extra bond in, and that bond represents 2 electrons. So that's why we end up with CnH2n. That's how that equation's somewhat derived. All right, so that means if I have 6 carbons, well, the hydrogen here, 6 times 2, is going to be 12. So if it meets that template, it could be, there's the magic term, could be an alkene. All right. Now, the problem here is that this also, in the last module, was the template for cyclo groups. Yeah, cycloalkanes also met the same template. And the reason is because this ring structure that we were drawing and studying at the time, well, it had to connect on itself. And in order to connect on itself, we had to take away 2 electrons. So C6H12 could be an alkene, or it could be a cycloalkane. All right, and I did that annoying-wise just so I could get your attention, and I hope that it worked. So C6H12 and this template, that CnH2n, it is not a confirmation. It is a could be one of these and could be one of these. And that's the problem with this equation, the way that they introduce it. They make it seem like it's so important and you have to know it and you have to know how to use it. But rarely do we even bring this up in the world of organic chemistry or in a laboratory science. All right, we just hardly ever do it, folks. And the reason is because so many things that we will learn about in the future will meet these templates that we are talking about here. So in a way, it doesn't quite make sense, but in the very beginnings of organic, it kind of does, because it gets you used to looking at carbons and hydrogens and having an association between the relationship of each other. All right. Now, alkenes can form cycloalkenes. All right, so this is not a problem. So what this would mean is like a 6-membered ring here, and with this 6-membered ring, I could get a double bond in that. That's not an issue. And if I do that, then we have another template that we go by, and this is going to be a CnH2n. Guess what? Well, let's think about it. If alkanes were 2n plus 2, and then we took away 2 electrons to make a ring, right? And we ended up with CnH2n. Well, we need to take away 2 more electrons to represent the double bond, don't we, if both of them are there? So this is going to be a 2n minus 2 at this point. So there is another template that we can go by, and this is a very good sign that it could be a cycloalkane, or alkene. Sorry, not a cycloalkane, an alkene. All right, so let's talk about the very simplest alkene that we have in this world of a new group of family of compounds. And this is a carbon double bonded to a carbon. And then off of this one, you know, it needs 4 bonds. So we'll draw 2 more hydrogens on each side, and there we go. All right, so if we use the rules of IUPAC that we've talked about before, this carbon to carbon, there's 2 carbons there, and these 2 carbons represent ethane, doesn't it? I mean, that's typically what we would have named it if it was a single bond. Well, we use the same words. It's the same language for double bonds. We just have to change it a little bit. And what we change, hope that you're pretty clever, this ANE represents alkane. All right, so if we erase this A and we put an E here and we call this ethene, then that ENE represents alkene. And that's the family of groups of compounds that we're talking about. So again, once more, we assign the ending of the functional group parent name that we want to look at to the main name of the compound. So this would be called ethene. All right, so a little bit of maybe review of the first lecture. I told you this was a build-up process. We start with basics, and it just keeps building on top of itself more and more and more and more. And here's an image of a double bond once again. So this double bond, you need to keep in mind, is a sigma bond. All right, so there is the initial bond that we have between the 2 carbons, and the double bond characteristic that we are focused on in this lecture, that we are focused on naming in this lecture, we have to keep in mind how it's formed. And this carbon will have a p orbital, and that p orbital will have an electron that can participate in sharing. And this carbon will also have a p orbital. All right, so there's 2 lobes of a p orbital. So this overlap of those p's will give me the double bond. Now, here's the problem. This is why I bring up the picture, because a lot of people get confused. The way that I've just drawn this, it almost would make people think triple bond, because they see a line here, and they see a line in the center, and they see a line at the bottom. That is not a triple bond. Okay, this is representation of a double bond, and the reason is because the single bond in the center is your first one. That's the first glue that holds the 2 carbons together. This p orbital, you have to keep in mind, it's all or none. So the p overlap, the top lobe and the bottom lobe, that overlap comes as a package. Okay, you don't treat it separately. So the overlap of that p orbit with the top and bottom piece, that is your second bond. And that's where the double bond comes from. If this was a triple bond, what I'm trying to tell you is that another p orbit with a top lobe and a bottom lobe, or one that points out and away from you, would have to be present. And that bottom piece and top piece would have to overlap, and that would create the third bond that we would call a triple bond. So again, don't let this diagram confuse you, as it does most people. This p overlap represents 1 bond in total. That top lobe and bottom lobe, you get all or you get none, and you keep them together, and you represent that as 1 glue, extra glue, that holds the carbons together. And then this one would be our second. All right. Okay, so let's go and talk about maybe some of these other alkenes, and start talking about ways to name them and so forth. So let's kind of just build up on what we've done already. So we'll do a carbon double bond carbon to a carbon. Now I can go through and draw in the hydrogens that I need. So this needs 2 more to get a total of 4. This one needs 1 hydrogen to get a total of 4, and this one here needs 3. So let's say that I have to draw this structure, or name the structure, sorry. Or let's say that I drew it as a skeletal structure. This is what it would look like. Okay, the first two carbons have a double bond, and then I don't have one. It's a single. So how do we name it? Well, 3 carbons is called prop. We learned that last time. And I normally would end this with ANE, but there's a double bond here, and that double bond is an alkene. So I need to end this in ENE. So this is a propene. All right, well, where does that double bond happen? Well, here's carbon 1 and carbon 2 and carbon 3. So this double bond first happens at carbon 1, right? Carbon 1 has a double bond on it. So this is going to be called a 1-propene. You can leave the 1 off and just call it propene, and we would know what you mean by that. So that's perfectly okay. Or if you wanted, some people write the word prop, and then they hyphenate it and put a 1 there and write the ENE. So that way you know for sure that that 1 goes to the double bond that's in the structure. All right, so there's just another example of another alkene and applying the rules that we already knew from the last lecture module all over again. So in a way, this is a blended lesson on incorporating 1 or 2 new things, but a review of everything that we've talked about before. All right, so let's take a look at another carbon, and this time let's go here. So I'm leaving off the hydrogens here. If you don't want to leave off the hydrogens, this would be a CH3, and this carbon would be a CH because there's 3 bonds to it. It needs a 4th. And then this carbon would be a CH. So again, 3 bonds, leaves off a 4th. There's the hydrogen. And then my last one is CH3. So sometimes you might see Blackboard or an assignment draw the structure this way. This is a key indicator that we have a double bond that's there, CH to CH, all right? And sometimes they might include that double bond in there. They might not, they might. But now you know what that represents if they leave it out. It's understood to be there if that's what they do to you. All right, so let's go back and name it. Here we've got 4 carbons, and those 4 carbons, that's called a bute. And this bute normally would have been a butane, but now it's a butene because of the double bond. All right, so I need to number closest to the end of the double bond. And here it doesn't really matter. I'm going to get a 1, 2, 3, 4, no matter which way I go. It's still going to be a 2-butene. All right, so on carbon number 2, that's where my double bond happens first. And again, I can hyphenate it here on the end. I don't do that, but you could, and I count it right. If you left off the 2, you're wrong, because I would assume that it's a 1. And a 1-butene, because you did not write the number, it does exist, and it looks like this. So 1, 2, 3, 4, there's bute, and on carbon 1, I have the ene, and on carbon 1, I have the double bond. So that is what that structure would look like. All right? So hopefully you feel a little okay with what you're seeing right now. It's mainly a review of all the rules that we've learned before, but we have modified it just a little bit at this point to incorporate the ENE ending. And that ENE represents the double bond. Now, let's see how the rules change if we have a ring, right? I told you that alkenes could make a ring without a problem. So let's go through and draw something that looks like this, and there we go. Okay, so this is a ring structure. Normally, you would call this a cyclo, right? And we still do it here. There's no difference. If you look at the total number of carbons, 1, 2, 3, 4, and 5. So this is a cyclopent something. And it normally would have been a pentane in the last lecture module. But now we have a double bond. So we know it's not a pentane, it's a pentene. So this is a cyclopentene ring. On carbon number 1, because it's a ring, I can start wherever I want. I'm just going to put carbon 1 right there. It's understood to be a 1. So 1 cyclopentene. Again, I can leave that number off, and it's understood to be there. Or I could separate cyclopent dash 1 dash ene, and that would also be acceptable. All right. Here's another example. Here is another ring structure, and I'll draw the double bond at that location. So if we take a look at the way this is ordered, 1, 2, 3, 4, 5, and 6. So this is a cyclohexene, right? Because there's a double bond involved. And I can number this wherever I want to start numbering it. I'll just do it there. So that will be my one spot. And this would be 1 cyclohexene, or simply cyclohexene, or cyclohex-1-ene. Again, that's also acceptable if that's the way that you see fit. All right, so hopefully, again, you're feeling a little bit better, you're feeling a little bit more comfortable, and now you understand why I blend these two lecture modules together into a test for you, because they are very strongly related. It's the same nomenclature rules, it's the same process, everything is identical except for the modification of the ENE at the end. All right, a term that I want to bring out here before we go a little bit further, and this term is called saturated and unsaturated. Okay, so in the world of food chemistry, you will often find this term saturated and unsaturated listed on a nutrition label, and it's there for a reason. It's talking about the organic that's associated with the foodstuffs that you're eating. So what types of compounds are on the inside? What types of organics are there and are present? What types of compounds are you putting into your mouth and you're chewing up and you're digesting? So saturated is really in reference to an alkane. So what that means is that all of the bonds are single bonds, carbon-carbon single bonds in a saturated molecule. In unsaturated molecules, these are typically the worlds of alkenes, and I'm going to put others here because we don't know what those others are, right? We just know alkane and alkene at this point, and that's it. So these are carbon double bonded carbons. So whenever we see these double bonds, those double bonds, if they were not present, would be a single bond. And more hydrogens could be added onto those carbons, and that's why we call it unsaturated. So saturated is in reference that all of the carbons have the maximum number of hydrogens that they could ever have. And unsaturated basically means that these carbons could take on more hydrogen. All right, but the only way they could take on more hydrogen is if they destroy that bond and open up a site of attachment that more hydrogens can go on at that point. So unsaturated is the family of alkenes, and saturated are the family of alkanes. It's one of the differences that we like to talk about. It's one of the differences that really do apply to your real life every single day that you eat something, look at a nutrition label, and so forth. And also other reasons that we talk about saturated and unsaturated in a lab environment. Okay, something else that I want you to keep in mind is that we also talked about different functional groups. I'm going to list those up here too because they're going to come back. And those functional groups were called an amine, and that amine was an NH2 group. It was an alcohol, and alcohols are OH groups. They were ethers, and ethers are ROR groups, and they were alkyl halides. All right, so alkyl halides were RX, and X represented fluorine, chlorine, bromine, iodine, and so forth. Okay, so now we can add on to this list, and we can add on alkenes. And alkenes are carbon double bonded carbons. So we can add another what we call functional group into our discussions of compounds and the nomenclature of compounds. And quite honestly, folks, it's not uncommon to have an alkene and an ether, or an alkene and an alcohol, or an alkene and an amine, or an alkene and an amine and an alcohol. Okay, you see where I'm going with this? So we're going to start off simple. We're going to start off with just focusing mainly on double bonds first, and we're going to get used to naming those. And then we might start slapping on these other functional groups that we've talked about before, and we'll figure out how to incorporate all of that into the names of the compounds, because they are going to show up. You are going to see those in those assignments, and we have to be comfortable with naming those when we do them. So we're going to keep it simple, back to basics, and we're going to go to alkenes first. And then later on in the lecture series, we're going to go back and we're going to start including these other functional groups that also need to be named and prioritize them the proper way. Okay, so that's where this lecture video is going to stop. In the next one, we'll continue on and we'll talk about the IUPAC nomenclature rules again. I think we kind of already done it, but we'll do another review and we'll go through and we'll start naming some of these organic molecules that I might see.